Welcome back. In this section, we'll be looking at graphing our basic shapes from section 3.1, this time with transformations applied to them. So by transformations, I'm referring to shifting the graph, or maybe stretching the graph, or maybe reflecting the graph. We're going to start off by looking at these transformations one at a time, and then later on we'll look at functions where we've got multiple transformations. To begin with, the first transformations we're going to look at are shifts. Starting with the vertical shift, which we're going to recognize if we have our function with an amount added on at the end or subtracted at the end. Amounts that are added on mean that we've got a vertical shift upwards by that many units, and an amount subtracted at the end means we have a shift downward by that many units. And what this is going to do, of course, is going to adjust or affect our y-coordinate, because our y-coordinate affects how much up or down we go. So if we're shifting it up by k units, we would be adding k to all of our y values. And if we're shifting it downwards by k units, we're subtracting k from all of our y values. So to look at this first function that we've got, the absolute value of x plus 2. So I recognize that this is a vertical shift since I have my basic shape, absolute value of x, with an amount added on at the end. So that this plus 2 means that I'm going to be shifting my graph upwards by 2 units. So I'm going to do this in two stages. I'm going to first start by graphing my basic shape, y equals absolute value of x, and then I'm going to graph the transformed version afterwards. So absolute value of x, we know that that passes through its three good points, 0, 0, 1, 1, and negative 1, 1. And I know that the graph has this kind of a shape. There we go. And as always, whenever I'm doing any of these graphs, I'm going to be doing well-labeled graphs for all of them. So even my basic shape, I'm going to make sure that I label the important points and that I've labeled the function itself. So there we go. I've got my graph of y equals absolute value of x, and I've got its three good points plotted and then the graph labeled. And now for y equals absolute value of x plus 2, the plus 2 is shifting our graph upwards by 2, and I'm going to do that by adding 2 to all of our y values. So 1, 1, I shift that upwards by 2 units to get 1, 3. 0, 0, I shift upwards by 2 units to get to 0, 2. And negative 1, 1, I shift that upwards by 2 units to get to negative 1, 3. And then I just have to draw my lines and finish off my labeling. So reminder, of course, that all of the points that are not on the x-axis or y-axis at tick marks, all of those points that I plot, I do need to label. So 1, 3 needs to be labeled. Negative 1, 3 needs to be labeled. 0, 2, I can label it if I want to, but I don't have to because it is at a tick mark on the axis. I also have to remember to label the equation itself. So I've labeled this. This is the graph of y equals absolute value of x plus 2. Okay, so now we've looked at vertical shifts. Next up is horizontal shifts. One thing that we're going to see is that for all of the horizontal transformations, they work in the sort of opposite way that you would expect them to compared to the vertical transformations. So with vertical shifts, a positive number meant shift upwards. With vertical shifts, a negative number meant shift downwards. Here with horizontal transformations, a negative doesn't mean a shift to the left, it actually means a shift to the right. So here, notice the difference. Rather than having a number added or subtracted from the entire function, I have a number that's being added or subtracted just from the x itself. So when I have a number that's subtracted from the x, we're shifting to the right. When I have a number that's added to the x, we're shifting to the left. So just to give you an example here, we've got this y equals x minus 1, the whole thing squared. So here, this is not a minus 1 added on at the end. If we'd had a y equals x squared minus 1, that would be a minus 1 just added on at the end of my squaring function. That would mean going down by 1. Here, on the other hand, we have the 1 being subtracted from the x before we've done the squaring. So this is not attached to the entire function. This minus 1 is attached to the x. And that would mean we'd be shifting not down 1, not to the left 1, but rather we're shifting to the right by 1. That the minus 1 means we're going to be adding 1 to all of our x values. So I'm going to do the same sort of graphing that I did before, which is I'll start with my basic shape. In this case, I'm going to graph y equals x squared. And then once I've done that, I'll graph y equals x minus 1 whole thing squared by adding 1 to each and every one of my x coordinates. So I'll start off with my basic shape, y equals x squared, which has the same 3 good points that absolute value of x did. Just more of a curvy shape rather than a pointy straight line kind of a shape. I'm going to label the equation, and I'll label the points. And there we go. We've got our basic shape accomplished. Now for our transformed version, y equals x minus 1 whole thing squared. We're shifting that to the right by 1, so we're adding 1 to all of our x values. So instead of 1, 1, we'll have 2, 1. Instead of 0, 0, we'll have 1, 0. And instead of negative 1, 1, we'll have 0, 1. And then there we go. We just need to label our points. And in this case, the only point that I have to label is 2, 1. The other 2 points, those are all at the x or the y-axis at a tick mark. So I don't have to label those. And there we go. We've got our transformed parabola that's been shifted to the right by 1. Okay, so we've talked about shifts up and down. We've talked about shifts left and right. The next thing to talk about is stretches. So first we're going to look at vertical stretches, and then we'll look at horizontal stretches afterwards. Same sort of thing as before when we were talking about a vertical shift. That was a number added to the entire function. A vertical stretch is a number multiplied by the entire function. So if we're talking about a positive number, then that is only going to refer to a vertical stretch. We'll see later on that if the number in front is negative, that has a second meaning to it. The idea here is that we'll be taking our function's y values and multiplying all of them by whatever that number is. So that means if the number is a large number, we'll be stretching our graph vertically. And if the number is a small number, between 0 and 1, we'll be compressing our graph. So a couple of examples of what I mean here. If we're looking at the y equals 2x cubed, that's my x cubing function all multiplied by 2. I would be multiplying all of my y values by 2, which makes my graph 2 times larger, as opposed to 1/3 x cubed, where I'd be taking all my y values and multiplying them by 1/3. So that means I would be making my graph 1/3 as big as it was before, or you could phrase it as 3 times smaller. It will be compressed. Anyhow, what we're going to be doing is this graph of y equals 2x cubed. So I know that this is a vertical stretch by a factor of 2. So I know that I'm going to be taking all of my y values and multiplying them all by 2. So I'll begin by first graphing my basic shape, y equals x cubed, which goes through 1, 1, 0, 0, and negative 1, negative 1. And then now to do the vertical stretch, I'm just going to take all of my y values and multiply them by 2. So instead of 1, 1, I'll have 1, 2. Instead of negative 1, negative 1, I'll have negative 1, negative 2. And that point 0, 0, since its y-coordinate is 0, multiply anything by 0 and it stays as 0. So now I'll have 0, 0, 1, 2, and negative 1, negative 2 as my 3 points. And we label our function, and there we go. We've got our graph nicely made. And our graph is stretched vertically by a factor of 2. It's 2 times taller than the original graph was. For horizontal compressions and stretches, kind of the same thing as before, we're going to do the opposite as to what we did back for the vertical version. So for a vertical version of stretching, large numbers meant we were getting bigger and small numbers meant we were getting smaller. Here it's the opposite. A large number in front of our x means we'll be getting smaller. So for example, this 2x does not mean we're going to be 2 times wider. It means we're actually going to be 2 times narrower. And something like a 1/2 x, instead of being 1/2 as wide as it originally was, it's actually going to be 2 times wider. What we'll be doing is, instead of multiplying each value of x by whatever this number a is, we'll be taking each x and dividing it by whatever the value in front is. So again, kind of think back to what we did for our horizontal and vertical shifts. For vertical shifts, we did exactly what we saw. If there was a +5 at the end, it meant add 5 to all the y values. But for a horizontal shift, if there was an x minus 5, we would be, instead of subtracting 5, we would be adding 5. For vertical shifts and, for vertical stretches and horizontal stretches, kind of the same thing. The number we saw in front of our function, the vertical stretch, we multiplied our y value by that number. But for a horizontal stretch, whatever number we see in front of the x, instead of multiplying by that number, we'll be dividing by that number. So for this square rooting graph, I have a 2 in front of my x, which means that when I'm thinking about graphing it, I'm going to now divide each x value by 2. Which means that we're going to be 2 times narrower than the original function would be. So let's get ourselves graphing here for our y equals square root of 2x function. Basic shape for our square root is that it goes through 0, 0, 1, 1, and 4, 2. I'll just label these points. And then for my square root of 2x, I'll be taking all of those x values and dividing them by 2. 0, 0, if I divide the 0 by 2, I still get 0. 1, 1, if I divide 1 by 2, I get 1/2. And then for 4, 2, if I divide the 4 by 2, I get 2, so the point 2, 2. So we've compressed our function horizontally. It's 2 times narrower now. Okay, so we've done 4 out of the 6 transformations. We've done vertical shifts and stretches. We've done horizontal shifts and stretches. The last thing to talk about are reflections. And for reflections, that's actually accomplished at the same time we do our stretches. If you had a -1 in front of your function, you would be multiplying all of your y values by -1. And that's going to flip all of your y values in the x-axis. Anybody who had a positive y value originally will now have a negative y value, and anybody who had a negative y value originally will now have a positive y value. Because it's done by that number in front of our function, the one that also would have controlled our stretching, that means that for vertical flips and vertical stretches, we're really going to do them at the same time. So if we're looking at this function y equals -3x squared, the 3 is going to make our graph 3 times taller, and the negative is going to make it also flipped. But both are going to be done at the same time, because what we're going to do is we're going to multiply every y value by -3. So by multiplying each y value by -3, we're just sort of doing two things at the same time. We'll be stretching and also flipping. So basic shape, y equals x squared, as always, goes through 0, 0, 1, 1, and -1, -1, 1. And now to do my transformed version, I'm going to take all of my y values and multiply them all by -3 to get my graph of y equals -3x squared. So the first point, 1, 1, when I multiply the 1 by -3, I get 1, -3 as my point. 0, 0, the y value is 0, so when I multiply it by anything, it stays as 0. And then finally 1, 1, when I multiply its y value by -3, I get -1, -3. So now we have our stretched parabola, and now pointing downward rather than pointing upward. And I just need to label those points, and then we're finished. And then lastly, the last transformation to talk about, the horizontal flips, flipping things in the y-axis. Not a surprise, you'll do that at the same time you do your horizontal stretches. So if we had a negative number in front of the x, that would change all of our x coordinates from positive to negative or negative to positive. So when we see something like this y equals square root of -1/3 x, what we're going to be doing is dividing each x by -1/3. And if you divide each x by -1/3, that's the same thing as multiplying each x by -3. So that means that what we're going to do is change all of the signs of all of our x values from positive to negative, and all of our x values will be 3 times bigger, which means we're going to have a square rooting function that's been stretched horizontally and also reflected. So starting off with my basic shape for my square rooting function, as always, going through 0, 0, 1, 1, and 4, 2. And just labeling those points. There we go. And then lastly, to do my transformation to get my graph of y equals square root of -1/3 x. As I said, we're going to be taking all of our x values and dividing them by -1/3, which is the same thing as multiplying by -3. So 0, 0 is now the same thing as 0, 0 was, because when we multiply x by anything, it's going to stay as a 0. But for 1, 1, when I divide that x coordinate by -1/3 or multiply by -3, that gets me the point -3, 1. And when I take 4, 2, takes that x coordinate of 4 and divide by -1/3, which is the same thing as 4 times -3, that gets me a new x coordinate of -12. So I now have points -12, 2 and -3, 1. Just going to try to redraw my curve here to make it look a little less like a straight line and make it look a little bit nicer. And I didn't really succeed, but that's okay. The thing that I like to tell everyone repeatedly when we're doing all this graphing, that the whole point of why we're doing all this labeling is, number one, to communicate something to whoever's reading, but also to make up for any flaws that we might have in our graphing skills. As you might notice, I am not the best at drawing things, and that's fine, because since I've labeled this as the square root of -1/3 x, even though it might not look perfectly like a computer might graph or a graphing calculator might do. At least somebody who's looking at this graph knows my intention. The intention is to have a stretched and flipped square rooting function. So there we go. We've talked about all 6 of our basic transformations.